Greetings everybody, and today we're going to be using complex analysis to evaluate the alternating Basel problem. So that's the infinite sum running from k equals 1 to infinity of minus 1 to the k minus 1 over k squared. So if you've watched my previous videos on the Basel problem, you'll know that what we did is we defined some function f of z in order to contour integrate over. And the nice thing with contour integrals is that you can use Cauchy's residue theorem to say that the contour integral over some contour, let's call it c, of this function f of z that we're going to figure out later is equal to 2 pi I times the sum of the residues of our function f of z. So our goal is to kind of interpret this sum that we have as some kind of sum of residues, because if we can somehow make this a link, then we can transform the sum of the residues into some kinds of contour integral that we can evaluate. So what is this function f of z over here? Well, in the case of the Basel problem, what we did is we took the function pi times the cotangent of pi z and we multiplied it by the thing inside of the sum. So that would be 1 over k squared in the case of the Basel problem. And the nice thing with using the cotangent function over here is that it generates poles at the integers, and when you have poles at the integers you can calculate the residues at each of those integers, and it turns out if you have this kind of multiplier in front of 1 over, this should be z squared, so 1 over z squared. If you have this multiplier out in front of this function that's being multiplied, if you take the residue at those integers of our function f of z, it spits out whatever you have inside of the sum, so 1 over k squared. So you take this 1 over z squared and you evaluate it at each of those integers of k. So that was the case for the Basel problem. It won't actually work too well for this alternating Basel problem because, well, we're alternating, and in order to kind of fix that, instead of using the cotangent function, we're going to be using the cosecant function. So we're going to let f of z be equal to pi times the cosecant of pi z times 1 over z squared. And this cosecant will generate the alternating terms for us. So now I want to show that the residue at each of those integers, so at z equals k, of our function f of z is indeed equal to this 1 over z squared evaluated at each of those k values, so at each of those integers, but it's also alternating. So what is the residue of this thing? Well, notice that cosecant is just 1 over sine of z. So of course now sine of z has zeros at all the integers. And the nice thing about sine is that it's an order 1 0, which means when you differentiate sine and you plug in those integers, you no longer get 0. So you differentiate it once, plug in each of those k values, those integers, and you don't get a 0 anymore. So that means sine is an order 1 0, which means when you take its reciprocal, it's an order 1 pole, so it's a simple pole. So we can just use the limit representation for simple poles. So the residue at z equals k is the limit as z approaches k of z minus 12, so z minus k, times our function f of z. But I'm going to rewrite f of z as being pi over the sine of pi z times 1 over z squared, like so. Okay, and now notice that we can do a little bit of L'Hopital on this z minus k and sine of pi z, because as z approaches k on both of those, you're going to get 0 divided by 0, which isn't too great. Also, I'm going to bring up this pi out to the very front. So now we have the limit as z approaches k. And I'm also going to split the limit up. So we're going to take this limit and the limit on this other part over here. So the limit as z approaches k, let's differentiate the top, that's going to be 1. Differentiating the bottom, that's going to give us pi times the cosine of pi z. And now we also have the limit as z approaches k of 1 over z squared. And now what is this going to give us? Well, notice that pi and pi will cancel each other out. And if you take the limit as z approaches k on this cosine of pi z, what you end up getting is minus 1 to the k. Because, for example, if k is 0, then cosine of 0 is 1. If k equals 1, then cosine of just pi is minus 1, so it kind of alternates like that. And then finally the limit on this part, that's going to give us 1 over k squared. So overall, this is minus 1 to the k divided by k squared. And you may notice, well, this doesn't really quite fit what we have initially. We needed a k minus 1, and the reason why we need a k minus 1 in particular is so our first term is positive. So in fact, that's not too difficult to fix, because all we have to do is to multiply a minus 1 everywhere over here. So if we multiply a negative 1 inside of our function, so let's chuck a negative in right there, then we're going to get a negative here, and then let's say a negative out the front, and then another negative, and you see negative 1 times minus 1 to the k, that's really the same thing as minus 1 to the k minus 1. So instead of choosing f of z just to be the thing without the negative, we're just going to place the negative there in order for the final result to match up what we have inside of the sum. And I want you to realize one small detail. I said that k was any integer before, but it actually can't be 0, because if you take a look on this function, is at 0 we have an order 3 pole, because we have an order 1 pole generated by this cosecant, and we also have an order 2 pole because we have 1 over z squared. So overall we have an order 3 pole at 0, so this kind of calculation of the limit doesn't really work at 0. So technically k over here is an integer, and we're excluding 0. So we know what the residues at the integers are of this function. Let's just write it over here. So the residue at z equals k, where k is an integer without 0, of our function f of z, that's going to give us minus 1 to the k minus 1 over k squared. And now let's try to figure out the residue at z equals 0, because we kind of want to know what the residues are at all the integers. So the next step is to calculate the residue at z equals 0 of f of z, and what we have to use the representation of the limit for higher order poles. So what we're going to do is we're going to take a 1 divided by the order of the pole minus 1, and then we're going to take the factorial of that, and then we're going to take the limit as z approaches the poles, as z approaches 0 in this case, of the derivative, but we don't just take one derivative, we take the order of the pole minus 1, so in this case it would be the second derivative of z minus the pole, so z, I guess I'll write it out, z minus 0 cubed, times our function, which is minus pi, times the cosecant of pi z, times 1 over z squared. And you can check out my derivation of this formula in the link below, or maybe I'll link it up here. I've done a proof for that. So this is quite a messy formula so this is quite a messy result that we have here, but let's try to clean things up as much as we can. There's a couple things we can do. So let's go down one line. First of all, 1 over 3 minus 1 factorial, that's exactly 1 over 2 factorial, which is just 1/2. So we have 1/2 out the front. Then we have the limit as z approaches 0, and now for the derivative, 3 minus 1 is 2, so we just have the second derivative with respect to z. And now over here we have z cubed, so z minus 0 is just z, and then z cubed is, well, z cubed. We can cancel out a little bit with the z squared over here. So z cubed is divided by z squared, that just leaves us with the z. So we have pi times z times the cosecant of pi z times 1 over, actually that's gone, so we just have pi z times the cosecant of pi z. And of course we still have this negative, so let's chuck that up to the front. Alright, very nice, and now what can we do? What I want to do is I want to rewrite this cosecant as 1 over sine, because we're going to be expanding things out in terms of Taylor series later on, which will be quite fun. So we have minus 1/2, limit as z approaches 0, second derivative of pi z over the sine of pi z. Okay, and now we're going to expand out sine in terms of its Taylor series, and you'll see why we're doing this later. So now we have minus 1/2, limit as z approaches 0, second derivative of pi times z divided by Now we have the infinite sum. Now let's choose an index, let's call it j. So j going from 0 to infinity of -1 to the j. Now for sine is an odd function, so we have odd powers, so we're going to have 2j plus 1 down here, and then our argument, which is pi z, to the 2j plus 1. Alright, very nice, and notice that we have a factor of pi z up here, which can cancel out down here, so we're going to subtract off 1 from the exponent and get rid of this up here, like so. Alright, and let's actually write out the first couple of terms of this series. So now we have 1/2 limit as z approaches 0, second derivative of 1 over, and now if let's plug j equals 0 in, well, we're just going to have pi z to the 0, which is 1, and then everything else down here should give us 1. So we just have 1, and then this is an alternating series, so now we have a minus. Our next term is j equals 1, so if we plug j equals 1 into here, we're going to have pi z squared. And then down here, we're going to have, let's see, we're going to have 3 factorial, which is 6, so we have -1 over 6, and then pi times z squared. And let's do one more actually. So we're going to have plus next, and then at j equals 2, well, -1 squared is 1, and then we have 2 times 2, which is 4, and then 4 plus 1, which is 5, so 5 factorial, which is 1 over 120, and then pi z to the 4. And then this just keeps going, so this infinite series continues. Alright, and why did we do this over here? What I want to do now is to kind of turn this reciprocal of a polynomial, I guess, into a polynomial. So we want to turn this weird reciprocal of a power series into another power series itself. And the reason for doing so is we want to take a second derivative, and taking derivatives of polynomials is nice, and taking derivatives of this stuff right here isn't so great. So that's why we're doing this series expansion. And we also have the limit as z approaches 0. So as z approaches 0, a lot of the higher order terms will actually cancel out. So it's nice if we can kind of transform this into some kinds of power series. So let's keep going. Alright, so now what do we have? Let's write this as -1/2, and we have the limit as z approaches 0 of the second derivative with respect to z. And now how can we turn this into some kinds of polynomial? Well, notice that we can use the geometric series for this, because we can kind of interpret this as 1 over 1 minus some kind of junk, let's call it x. And we know that if x is between -1 and 1, so its radius of convergence is 1, then we can write this as the infinite sum running from j equals 0 to infinity of x to the j. And how do we know that the stuff in here is between -1 and 1? Well, it's because we're taking the limit as z approaches 0, and of course 0 is in the interval -1 to 1. So in fact this stuff is in the radius of convergence. So let's try to rewrite what we have over here into this form, and if we can do that, then we can use the geometric series. And the geometric series, well, in this case we can interpret it as some kinds of power series. So now we have the second derivative of 1 over 1, and then we're going to factor out a minus, so we're going to put out a minus, and then on the inside we're going to have 1/6 and then pi z squared, and then we factored out a negative, so this plus becomes a minus, so -1 over 120 of pi z to the 4 plus ... like so. Alright, and now we can turn this into a geometric series. So this is going to give us a -1/2 limit as z approaches 0 on the second derivative with respect to z of the sum running from j equals 0 to infinity of this stuff raised to the j power. So we have 1/6 pi z squared -1 over 120 times pi z to the 4 plus ... but all raised to the jth power. Okay, and now we more or less have some kind of infinite polynomial, so some kind of power series. And I want you to notice one thing. Whatever this series becomes, we can always write it in the form a0 times pi z to the 0, and then we have plus a1 times pi z to the 1 plus a2 times pi z squared plus dot dot dot. So we always have some kind of constant and then our argument in this case, which is pi z to each of those powers. And notice that we're taking the second derivative of this thing. So if we take the second derivative of this thing, well, this is a constant, so that's going to disappear. So we don't really care about anything that has a so we don't really care about constants in terms of this series. And then any terms of degree 1 will also get cancelled out in this second derivative, because if you differentiate it twice, you're left with whatever constants here, and then differentiating that again, then that constant is just going to vanish off to 0. And for terms with a degree 2, if you take a second derivative of, let's say, a quadratic term, that's going to reduce down to a constant. And the nice thing with having a constant is that once you apply the limit as z approaches 0, the constant isn't affected, but all the latter terms are, because the latter terms are what? A cubed pi z cubed. And if you take the second derivative of this thing, it's going to reduce down to a linear term. So we're going to have some kind of constant times z. And in the limit as z approaches 0, that's going to die off as well. So will all the other terms. So in fact, all we're really interested in is terms with a degree 2. So terms that are squared inside of the series. Because once we take the second derivative and take the limit as z approaches 0, those are the only terms that will survive the process. Everything else will just be 0. So let's take a look at the series again. What are the terms that are squared or have degree 2? Well, for j equals 0, well, this thing to the 0 is just 1, and if you differentiate a constant twice, that's a 0. So for j equals 0, nothing really interesting happens. Now if you let j equals to 1, well, this is going to become a 1, so it pretends that doesn't exist. And we have this kind of infinite series inside, and right over here, that's our quadratic term. So we have 1/6 times pi z, but the whole thing squared, and everything else has a degree higher, so we don't really care about that. Okay, so that's for j equals 1, and how about j equals 2? Well, if j equals 2, the smallest degree inside of this polynomial is a quadratic term, so something squared. And we have something squared that's also being squared again, because j is equal to 2. And that's going to result in the smallest degree being 4. And we're not really interested in that, because that's going to die off in this process. And in fact, for all j's that are greater than 1, we're just going to get higher and higher order terms, which we don't want. We just want this quadratic term. So the only thing that we care about is when j is equal to 1 and this specific term over here. So if we differentiate this, I guess, power series twice, what we end up is 1/2 times the limit as z approaches 0 on, well, what is the second derivative of this thing? Well, if you differentiate this thing once, let's see, you're going to get pi cubed over 3 times z, because this is pi squared times z squared, and just some basic power rule. And if you differentiate this thing again, so double diff it, the z will drop off, leaving you with pi cubed over 3. So we have the limit as z approaches 0 on pi squared over 3 plus a bunch of random higher order terms. So for example, we have some constant c2 times z squared plus c4 times z4 plus dot dot dot. And in the limit as z approaches 0, all those will disappear off to 0. The only thing that survives is the constant term. And well, we're just left with minus 1/2 times pi squared over 3, which is minus pi squared over 6, like so. Okay, so what did we find out over here? We found out that the residue at z equals 0, because remember, all that work was just to find the residue at z equals 0. So residue at z equals 0 on our function f of z is equal to minus pi squared over 6. So we have minus pi squared over 6, like so. Alright, so let's look at what we have on the complex plane. So imagine this is the complex plane, and we've figured out all the values of the residues that are not 0. It's just going to be minus 1 to the k minus 1 over k squared. So So those are all these residues over here. And we found the residue at z equals 0 as well, so over here. And we found that to be minus pi squared over 6. And now we want to use Cauchy's residue theorem. So ideally we want to enclose all these poles. So what we're going to do is construct a really big square, like so. And we're going to call this square Sn, so it has some kind of relationship with n, and as n grows really big, we can actually show that the contour integral over S sub n of f of z dz goes to 0 as n approaches infinity. And I'm not going to show that in this video. If you watch my Basel problem video, I go through a similar proof for it using the cotangent function instead of the cosecant function. But if you can understand the method I used in that video, proving it for this case, for this function over here, wouldn't be too difficult. So we know that the contour integral in the limit goes off to 0, which is nice. And let's use Cauchy's residue theorem now. So we have the contour integral over this S sub n of f of z dz is equal to 2 pi I times the sum of the residues of our function f of z. And the residues lie at the integers. So let's say z equals k, and k is the integers. Okay, we know that this thing in the limit goes off to 0, so technically there should be a limit out here. So this thing goes to 0, and we have the scalar 2 pi I, and 2 pi I is not equal to 0, so we can divide both sides by 2 pi I, leaving us with 0 being equal to the sum running along the integers, so k along the integers, of the residue at z equals k of a function f of z. And what are the sum of the residues? Well, we already know what these residues are, we just need to add them all together. So this is equal to now, first of all, we have the sum running along the integers excluding 0. So we know what this result is. This is for the integers excluding 0. So first of all, we have the sum running along the integers excluding 0 of the residue at z equals k of f of z. So that's all these guys right here. And we also have the residue at z equals 0. So we have to plus the residue at z equals 0 of a function f of z. Okay, and we know what the residues at z equals k are. So this is equal to, can I fit it in the camera? Hopefully I can. So this is the sum running along the integers excluding 0. Now the residue at z equals k that's not 0 is equal to minus 1 to the k minus 1 over k squared, and then we have plus the residue at z equals 0 is actually minus pi squared over 6, so that subtracts off pi squared over 6, and this is equal to 0. Alright, that's quite nice. Let's try to isolate the sum, because this sum is looking very similar to what we had at the very start. So now let's see, what do we have? Let's move this minus pi squared over 6 onto the other side, so we have now that the sum running from when k equals, well, k elements of the integers excluding 0 of minus 1 to the k minus 1 over k squared is now equal to pi squared over 6. Okay, and I want you to notice one cool thing. If you take a look at the set of the integers excluding 0, let's say on a real number line, then let's say this is 0, then you're hitting all these points here. So 1, 2, 3, 4, 5. And it's minus 1, minus 2, minus 3, minus 4, minus 5, and so on. And notice one cool thing. This is symmetric across 0, and so is this function inside of the sum. It's actually an even function. And we can show that quite easily if we let k be equal to minus j, for example, where j is a positive integer. Then what we get is minus 1, and then k, we let that be equal to minus j, so minus j minus 1, and then we divide that by minus j, but the whole thing squared. And notice one cool thing, the sign of this expression, so either negative or positive, depends on if j is odd or even. And let's say j is an even number, and you subtract 1 off from it, then it's odd. But if you remove this negative out the front, if j is even and you subtract, it's still also odd. So in fact, it doesn't matter if you have a minus or not out here, it's still going to give you either odd or even. And well, minus j squared down here, that's just j squared, so we have minus 1 to the j minus 1 over j squared. So in fact, the negative values, so the values on this side, are the exact same as the values on the right side. So in fact, this function inside the sum is symmetric across 0, and we can use a nice trick for that, because well, we know that if we take the sum for the positive integers of minus 1 to the k minus 1 over k squared, and then we add it with the sum over the negative integers, so z negative of minus 1 to the k minus 1 over k squared. Notice that if you add these two sums together, then you get the sum over all the integers excluding 0. We know that these two sums are going to be the exact same thing, and this is equal to pi squared over 6. So we can combine these two together since they're equivalent. So now we have 2 times the sum running along the integers of minus 1 to the k minus 1 over k squared, and that's equal to pi squared over 6. And the last step to do is just divide both sides by 2, and we get that the sum running along the positive integers, so this should be in positive integers, of minus 1 to the k minus 1 over k squared is equal to pi squared. Now we divide both sides by 2, so that's pi squared over 12. And this is in fact the very sum that we started with. So positive integers is the same as running from k equals 1 to infinity. So thus we've shown that this sum, the alternating Basel problem, evaluates to pi squared over 12. So that's pretty cool. The alternating Basel problem is exactly half of the value of the original Basel problem. So yeah, that's pretty much it for this video. I hope you guys enjoyed this little complex analysis excursion. But yeah, until next time, hope you guys have a wonderful day, and I'll see everyone later. Bye bye.